Hey folks, on this episode of the Encyclopedia, we're going to be taking a deep dive into photonic thrusters, explain how they work, and see the physics of the light engine. Could this power a spacecraft in the future? Well, you're in the right place. Don't forget to hit that subscribe button and ring that bell so you don't miss future videos. Let's get started. So what exactly are photonic thrusters? A photonic thruster is a type of engine that uses momentum of emitted photons or light particle, or its propulsion. Yeah, you heard it right, it's propelled by light. So if you think about it, a jet engine uses combusted gas in order to move forward. Air is taken in, fuel is sprayed in, ignited, catches fire. The amount of gas produced from the liquid fuel is then ejected outwards at a higher speed, and so the plane moves forward. Similarly, light engine. The reason why they exist is you don't need to carry any sort of onboard fuel. Well, you need to carry fuel in order to make the thing work, but still, there's no reaction mass used in the light engine. Like for example, in terms of a rocket, if you think about a rocket, it's got to carry its oxidizer, the fuel, and all of them, because nowadays we're using cryogenic rocket technology. But light engines seem more viable because nowadays if we can produce thrust from just electricity, well, that's a huge win because that works, and satellites maneuver on their own. If you think about it, they got solar panels, and if you can convert electricity to thrust, then you can actually maneuver satellites a lot easier and it's also sort of unlimited because the sun, and then solar panels will be able to convert that into electricity, and then the light engine will be able to push itself as it goes. That seems to be a work in progress for a lot of research labs who are trying to get this technology to work so that we can actually move stuff using just light without having to carry any sort of fuel around. Now let's get to the physics behind this. Energy equals mass times the speed of light. That means light, despite having zero mass, photons have no mass actually. Light, when it's emitted, can carry momentum. Photons are emitted from a source, and when they're reflected off a surface, they transfer their momentum to that surface. So it kind of exerts a force. This force, even though it's really tiny, it can propel a spacecraft. There have been examples where people have taken two mirrors and they've bounced photons around. That was a way where they fermented with light engines, and it kind of worked. But that requires two separate units. So the spacecraft itself doesn't contain the light engine, instead it just contains a mirror and the other end, which has the laser system itself and another mirror. But the only issue is that the spacecraft has to be within the range of that laser. And also, not only that, but if the spacecraft is traveling at relativistic speeds, which means relative to that of the speed of light, so I guess anywhere between 0.1 to 1 multiple of the speed of light, it's going to start experiencing something called the red shift. So what that means is that if you remember a cop car, if it's chasing down a bad guy and it goes right past you, you can hear the pitch of the siren increase as it comes closer, and it goes like so the frequency increases and then it decreases. That's called a Doppler shift. But in terms of light, if the object is moving away, well, then the light emitted by that object will have a red shift. That's why some stars, despite being a different color, tend to be a little bit more red compared to other stars because of the red shift in the universe. That's how we discovered that the universe is actually still exploding. Let's calculate how fast this laser pointer moves in space. I will assume that this laser has an output power of 72 milliwatts just to make the calculations easy. So now let's do the math. To calculate the velocity, we simply use the mass-energy relation derived by Albert Einstein, E equals mc squared. Now the laser power is 72 milliwatts, and the equation of power equals energy by time. Okay, so we're going to be rearranging the equation so that we can put momentum on the left side, the equal sign, and right hand side is we're going to be substituting values. So first we do E equals mc multiplied by c. So the mc is momentum of the light, so E equals momentum multiplied by the speed of light. Momentum is t, so rearranging it again, momentum equals energy divided by velocity. So above, I just said that power equals energy divided by time. If we change that around, energy equals power multiplied by time. So momentum equals power multiplied by time divided by the velocity of light. And so we're measuring over a period of 1 second, substitute 1. So the momentum equals power divided by the velocity of light. And substituting all the values now, momentum equals 72 milliwatts divided by 3 multiplied by 10 to the power of 8 meters per second. Now just simply calculating it, we get momentum equals 2.4 multiplied by 10 to the power of minus 10 kilogram meters per second. Oh, kilogram meters per second is the momentum unit, by the way. So the weight of the laser 303 is 120 grams. So the momentum experienced by the laser pointer is exactly the same as the light, because light is one that's exerting momentum, so that's why momentum of the light equals momentum of the laser pointer. This is, well, the third law of Newton. Just substituting everything in that equation, we get 2.4 multiplied by 10 to the power of minus 10 equals the velocity of the laser pointer, which we're trying to calculate, multiplied by 0.12. Alright then, so we're measuring in kilograms. After calculation, velocity equals 2 nanometers. Put it in space, and you measure the velocity after about 1 second. Well, at exactly 1 second, it's going to be 2 nanometers per second. While photonic thrusters hold great promise for interstellar travel, there are challenges, and one of the main issues is that they're really inefficient. The experiments that have done so far have, pushed only small objects and everything. The thrusters themselves require a lot of energy to even work, and not only that, but multiple mirrors makes it such that the spacecraft cannot really, it's only for orbit changes in the orbit at best, not like traveling through space. Well, if this technology does somehow work and we're able to travel in space, we're not going to be doing Star Trek, Star Wars type stuff because the efficiency is really low, and not only that, but the efficiency of a standard jet engine is also supremely high compared to what this can do, and even a normal rocket has a really good efficiency. So one good example of this technology is formation flying of multiple spacecraft. What happens is, in order to fly in a proper formation, a spacecraft has to be properly oriented and it has to be at a proper distance with the other spacecraft, otherwise it could just crash. In order to prevent that, there are several ongoing research projects aimed at improving the efficiency and practicality of photon thrusters. For example, researchers are using high-intensity lasers to generate a large number of photons and advanced materials with high reflectivity to maximize the momentum transfer from the photon. The future of photon thrusters is pretty good, yeah? With advancements in technology and better understanding of the physics involved, we could see photon thrusters being used in more and more space missions, but still really inefficient, and light produces really low momentum compared to, every other jet engine, rocket engine, etc., etc. But space is a vacuum, so there's no aerodynamic drag or anything. Work better in space than on the Earth. As we continue to explore the cosmos, innovative technologies like this will play a crucial role in our journey. So that's all for today. If you found this video informative, give it a thumbs up and share it with your friends. Till next time.